In mathematics, a countable set is a set with the same cardinality as some subset of the set of natural numbers. A countable set is either a finite set or a countably infinite set. Whether finite or infinite, the elements of a countable set can always be counted one at a time and, although the counting may never finish, every element of the set is associated with a natural number. Some authors use countable set to mean countably infinite alone. To avoid this ambiguity, the term at most countable may be used when finite sets are included and countably infinite, enumerable, or denumerable otherwise. The term countable set was introduced by Georg Cantor, who contrasted sets which are countable with those which are uncountable. Today, countable sets form the foundation of a branch of mathematics called discrete mathematics. Definition: a set S is called countable if there exists an injective function f from S to the natural numbers n equals 0, 1, 2, 3. If such an f can be found which is also surjective, then S is called countably infinite. In other words, a set is called countably infinite if it has one-to-one correspondence with the natural number set, n. As noted above, this terminology is not universal. Some authors use countable to mean what is here called countably infinite, and do not include finite sets. Alternative formulations of the definition in terms of a bijective function or a surjective function can also be given, see below. History: in the Western world, different infinities were first classified by Georg Cantor around 1874. Introduction: a set is a collection of elements, and may be described in many ways. One way is simply to list all of its elements. For example, the set consisting of the integers 3rd, 4th and 5th may be denoted 3, 4, 5. This is only effective for small sets, however. For larger sets, this would be time-consuming and error-prone. Instead of listing every single element, sometimes an ellipsis is used, if the writer believes that the reader can easily guess what is missing. For example, 1, 2, 3. 100 presumably denotes the set of integers from 1 to 100. Even in this case, however, it is still possible to list all the elements, because the set is finite. Some sets are infinite. These sets have more than n elements for any integer n. For example, the set of natural numbers, denotable by 0, 1, 2, 3, 4, 5, has infinitely many elements, and we cannot use any normal number to give it size. Nonetheless, it turns out that infinite sets do have a well-defined notion of size, and not all infinite sets have the same cardinality. To understand what this means, we first examine what it does not mean. For example, there are infinitely many odd integers, infinitely many even integers, and infinitely many integers overall. However, it turns out that the number of even integers, which is the same as the number of odd integers, is also the same as the number of integers overall. This is because we arrange things such that for every integer, there is a distinct even integer. A 2a4, a 1a2, 0 a 0, 1 a 2, 2 a 4. Or, more generally, na 2n, see picture. What we have done here is arranged the integers and the even integers into a one-to-one correspondence, which is a function that maps between two sets such that each element of each set corresponds to a single element in the other set. However, not all infinite sets have the same cardinality. For example, Georg Cantor demonstrated that the real numbers cannot be put into one-to-one correspondence with the natural numbers, and therefore that the set of real numbers has a greater cardinality than the set of natural numbers. A set is countable if it is finite, or it has the same cardinality as the set of natural numbers. Equivalently, a set is countable if it has the same cardinality as some subset of the set of natural numbers. Otherwise, it is uncountable. Formal overview without details: by definition a set S is countable if there exists an injective function f, Sn from S to the natural numbers n equals 0, 1, 2, 3. It might seem natural to divide the sets into different classes, put all the sets containing one element together. All the sets containing two elements together. Finally, put together all infinite sets and consider them as having the same size. This view is not tenable, however, under the natural definition of size. To elaborate this, we need the concept of a bijection. Although a bijection seems a more advanced concept than a number, the usual development of mathematics in terms of set theory defines functions before numbers, as they are based on much simpler sets. This is where the concept of a bijection comes in. Define the correspondence, AA1, BA2, CA3, since every element of A, B, C is paired with precisely one element of 1, 2, 3, and vice versa, this defines a bijection. We now generalize this situation and define two sets to be of the same size if there is a bijection between them. For all finite sets, this gives us the usual definition of the same size. What does it tell us about the size of infinite sets? Consider the sets A equals 1, 2, 3. The set of positive integers and B equals 2, 4, 6. The set of even positive integers. We claim that, under our definition, these sets have the same size, and that therefore B is countably infinite. Recall that to prove this we need to exhibit a bijection between them. But this is easy, using Na2n, so that 1 are 2, 2 are 4, 3 are 6, 4 are 8, as in the earlier example, every element of A has been paired off with precisely one element of B, and vice versa. Hence they have the same size. This gives an example of a set which is of the same size as one of its proper subsets, a situation which is impossible for finite sets. Likewise, the set of all ordered pairs of natural numbers is countably infinite, as can be seen by following a path like the one in the picture. The resulting mapping is like this: 0, 1, 2, 3, 4, 5, 6. It is evident that this mapping will cover all such ordered pairs. Interestingly, if you treat each pair as being the numerator and denominator of a vulgar fraction, then for every positive fraction, we can come up with a distinct number corresponding to it. This representation includes also the natural numbers, since every natural number is also a fraction n/1. So we can conclude that there are exactly as many positive rational numbers as there are positive integers. This is true also for all rational numbers, as can be seen below. Theorem: the Cartesian product of finitely many countable sets is countable. This form of triangular mapping recursively generalizes to vectors of finitely many natural numbers by repeatedly mapping the first two elements to a natural number. For example, maps to which maps to 39. Sometimes more than one mapping is useful. This is where you map the set which you want to show countably infinite, onto another set, and then map this other set to the natural numbers. For example, the positive rational numbers can easily be mapped to the pairs of natural numbers because PQ maps to. What about infinite subsets of countably infinite sets? Do these have fewer elements than n? Theorem: every subset of a countable set is countable. In particular, every infinite subset of a countably infinite set is countably infinite. For example, the set of prime numbers is countable, by mapping the nth prime number to n, 2 maps to 1, 3 maps to 2, 5 maps to 3, 7 maps to 4, 11 maps to 5, 13 maps to 6, 17 maps to 7, 19 maps to 8, 23 maps to 9. What about sets being naturally larger than n? For instance, Z, the set of all integers, or Q, the set of all rational numbers, which intuitively may seem much bigger than n. But looks can be deceiving, for we assert, theorem Z and Q are countable. In a similar manner, the set of algebraic numbers is countable. These facts follow easily from a result that many individuals find to be non-intuitive. Theorem: any finite union of countable sets is countable. With the foresight of knowing that there are uncountable sets, we can wonder whether or not this last result can be pushed any further. The answer is yes, and no, we can extend it, but we need to assume a new axiom to do so. Theorem: the union of countably many countable sets is countable. For example, given countable sets A, B, C. Using a variant of the triangular enumeration we saw above, A0 maps to 0, A1 maps to 1, B0 maps to 2, A2 maps to 3, B1 maps to 4, C0 maps to 5, A3 maps to 6, B2 maps to 7, C1 maps to 8, DO maps to 9, A4 maps to 10. Note that this only works if the sets A, B, C are disjoint. If not, then the union is even smaller and is therefore also countable by a previous theorem. Also note that the axiom of countable choice is needed in order to index all of the sets A, B, C simultaneously. Theorem: the set of all finite length sequences of natural numbers is countable. This set is the union of the length 1 sequences, the length 2 sequences, the length 3 sequences, each of which is a countable set. So we are talking about a countable union of countable sets, which is countable by the previous theorem. Theorem: the set of all finite subsets of the natural numbers is countable. If you have a finite subset, you can order the elements into a finite sequence. There are only countably many finite sequences, so also there are only countably many finite subsets. The following theorem gives equivalent formulations in terms of a bijective function or a surjective function. A proof of this result can be found in Lang's text. Basic theorem: let S be a set. The following statements are equivalent. S is countable, that is there exists an injective function f, SON. Either S is empty or there exists a surjective function g, NS. Either S is finite or there exists a bijection h, NOS. Corollary: let S and T be sets. If the function f, S at T is injective and T is countable, then S is countable. If the function g, S at T is surjective and S is countable, then T is countable. Cantor's theorem asserts that if A is a set and P, A, is its power set, that is the set of all subsets of A, then there is no surjective function from A to P, A. A proof is given in the article Cantor's theorem. As an immediate consequence of this and the basic theorem above, we have proposition: the set P, N, is not countable. That is, it is uncountable. For an elaboration of this result, see Cantor's diagonal argument. The set of real numbers is uncountable, and so is the set of all infinite sequences of natural numbers. Some technical details: the proofs of the statements in the above section rely upon the existence of functions with certain properties. In this section, functions that are commonly used in this role will be presented, but not the verifications that these functions have the required properties. The basic theorem and its corollary are often used to simplify proofs. Observe that N in that theorem can be replaced with any countably infinite set. Proposition: any finite set is countable. Proof: by definition, there is a bijection between a non-empty finite set S and the set 1, 2, n for some positive natural number n. This function is an injection from S into n. Proposition: any subset of a countable set is countable. Proof: the restriction of an injective function to a subset of its domain is still injective. Proposition: if S is a countable set and X a permol S, then SAX is countable. Proof: let F, SON be an injection. Define G, SAXN by G, X, equals 0 and G, Y, equals F, Y, plus 1 for all Y in S. This function G is an injection. Proposition: if A and B are countable sets, then A or B is countable. Proof: let F, AN and G, BON be injections. Define a new injection H, A or BON by H, X, equals 2F, X, if X is in A and H, X, equals 2G, X, plus 1 if X is in B but not in A. Proposition: the Cartesian product of two countable sets A and B is countable. Proof: observe that N is countable as a consequence of the definition because the function f, N given by f, m, n, equals 2m3n is injective. It then follows from the basic theorem and the corollary that the Cartesian product of any two countable sets is countable. This follows because if A and B are countable, there are surjections f, Na and G, N B, so Fa, G, N B is a surjection from the countable set N to the set A, B, and the corollary implies A, B is countable. This result generalizes to the Cartesian product of any finite collection of countable sets, and the proof follows by induction on the number of sets in the collection. Proposition: the integers z are countable and the rational numbers q are countable. Proof: the integers z are countable because the function f, z o n given by f, n, equals 2n if n is non-negative and f, n, equals 3an if n is negative, is an injective function. The rational numbers q are countable because the function g, z o, n are q given by g, m, n, equals m slash, n plus 1, is a surjection from the countable set z o, n to the rationals q. Proposition: if n is a countable set for each n in n, then the union of all n is also countable. Proof: this is a consequence of the fact that for each n there is a surjective function gn, n and hence the function given by g, n, m, equals gn, m, is a surjection. Since n is countable, the corollary implies that the union is countable. We are using the axiom of countable choice in this proof in order to pick for each n in n a surjection gn from the non-empty collection of surjections from n to n. A topological proof for the uncountability of the real numbers is described at finite intersection property. Minimal model of set theory is countable. If there is a set that is a standard model of ZFC set theory, then there is a minimal standard model. The Le-Paragraph-Inheim-Scullum theorem can be used to show that this minimal model is countable. The fact that the notion of uncountability makes sense even in this model, and in particular that this model M contains elements which are subsets of M, hence countable, but uncountable from the point of view of M, was seen as paradoxical in the early days of set theory. See Scullum's paradox. The minimal standard model includes all the algebraic numbers and all effectively computable transcendental numbers, as well as many other kinds of numbers. Total orders: countable sets can be totally ordered in various ways, for example, well orders, the usual order of natural numbers, the integers in the order. Other, the usual order of integers, the usual order of rational numbers. Note that in both examples of well orders here, any subset has a least element. And in both examples of non-well orders, some subsets do not have a least element. This is the key definition that determines whether a total order is also a well order. See also, Aleph number, counting, Hilbert's paradox of the Grand Hotel, uncountable set. Notes, Rudin 1976, Chapter 2, Camk 1950, pages 2, A. B. Lang 1993, A. Section 2 of Chapter 1, Apostle 1969, Chapter 13.19, since there is an obvious bijection between n and n equals 1, 2, 3. It makes no difference whether one considers 0 to be a natural number or not. In any case, this article follows ISO 31-11 and the standard convention in mathematical logic, which takes 0 as a natural number. Stillwell, John C., Roads to Infinity, The Mathematics of Truth and Proof, CRC Press, pages 10, ISBN 9781439865507. Cantor's discovery of uncountable sets in 1874 was one of the most unexpected events in the history of mathematics. Before 1874, infinity was not even considered a legitimate mathematical subject by most people, so the need to distinguish between countable and uncountable infinities could not have been imagined. Camk 1950, pages 3-4, Halmos 1960, pages 91, Avelsgaard 1990, pages 179, Avelsgaard 1990, pages 180, Halmos 1960, pages 92, Avelsgaard 1990, pages 182, Fletcher and Patty 1988, pages 187. References: Apostle, Tom M., Multivariable Calculus and Linear Algebra with Applications, Calculus 2, New York, John Wiley + Sons, ISBN 978-0-471-00007-5, Avelsgaard, Carol, Foundations for Advanced Mathematics, Scott, Forsman and Company, ISBN 0-673-38152-8, Fletcher, Peter. Patty, C. Wayne, Foundations of Higher Mathematics, Boston, PWS Kent Publishing Company. ISBN 0-87150-164-3, Halmos, Paul R., Naive Set Theory, D. Van Nostrand Company, Incorporated, reprinted by Springer Verlag, New York, 1974. ISBN 0-387-90092-6. Reprinted by Martino Fine Books, 2011. ISBN 978-1-61427-131-4. Kamk, E., Theory of Sets, New York, Dover, Lang, Serge, Real and Functional Analysis, Berlin, New York, Springer Verlag, ISBN 0-387-94001-4, Rudin, Walter, Principles of Mathematical Analysis, New York, McGraw-Hill, ISBN 0-07-054235-X. External links: Weierstein, Eric W., Countable Set, MathWorld.